I'm also very thankful for the talk invitation, and it's my big honor to give a presentation here today. My topic today is about towards versatile test time adaptation. Okay, let's begin. So first, I start from some background introduction of the deep learning. Yeah, the conventional deep learning pipeline firstly train a deep model on a pre-collected training dataset, and then keep all model parameters frozen during the whole testing phase. So this pipeline works pretty well when the testing data are drawn from the same distribution of the training data. It is known as in distribution. However, the world is always changing, such as simulation to real-world scenario change. The weather changes like from sunny to rainy to foggy, and sometimes the lighting changes like from day to night, and sometimes the scenarios changes from a city to a village. So it is hard to keep the testing distribution unchanged all the time, and we call this out of distribution domain shift. But unfortunately, under such out-of-distribution scenarios, the deep model may suffer from severe performance degradation. So a critical challenge we face is that we need adaptation when using these deep models in the real world. Actually, to generalize the model to out-of-distribution domains, techniques also have experienced three stages. The first stage is pre-training stage, such as training time methods like domain generalization, various data augmentation techniques that seek to enlarge the training distribution so that it may cover the potential domain shifts encountered during testing. And the second one is post-training fine-tuning, such as unsupervised or semi-supervised domain adaptation, which needs to conduct during the training on a pre-collected target data set. Sorry. Pre-collected target. The latest one is test time adaptation, which seek to unleash the model power during inference. And test time adaptation directly learns from the testing data. It does not need any label and can be performed in an online manner, where the samples come one by one. And it doesn't need heavy training, and that is relatively more green and effective. It also achieves good performance, and it can serve as a fundamental idea to support any pre-trained model. And this figure demonstrates the pipeline of test time adaptation. Test time adaptation is also more like human intelligence that continuously learn from the environments with few short or zero short signals. Given a source model and a batch or a single test sample, test time adaptation will keep update the model using the test data via some self-supervised or unsupervised learning objectives, such as entropy minimization, rotation prediction, contrastive learning-based objectives, and so on. However, although test time adaptation has demonstrated promising performance, its application in real-world deployment is still somehow limited. To bridge this gap and prompt the larger-scale real-world test time adaptation deployment, personally, I think the versatility is still a key step. And the versatility can also be split into two aspects. The first is task versatility, and this is also the main part of today's talk. Because prior test time adaptation methods still rely on specific design for different tasks. For example, the methods designed for classification may not applicable to regression tasks, thereby lacking versatility. And in this case, if we need to redesign a specific TT method when facing a given new task, it will be highly time-consuming and rely on expert efforts, thereby largely rendering its large-scale application. And then the second one I also want to mention is the device versatility. As we all know, the good performance of test time adaptation is mainly originated from the explicit learning on testing data via gradient backward propagation. However, this gradient computation is quite resource consuming, which is often only supported by high-performance GPU devices, rendering it being adopted on resource-limited embedded systems, such as the mobile phones, the robots. So next, we first discuss the task versatility of test time adaptation, for which we devise a self-bootstrapping method for versatile test time adaptation on various tasks. The prior TTA methods still lacking versatility and spatially reflected in the following aspects. Firstly, the entropy of self-learning-based methods like TENT aim to maximize the model's largest predicted logic. So this is applicable to image level and pixel level classification tasks, but are not applicable to regression tasks as there is no predicted logic. And it's also not applicable to object detection tasks, where we need to predict the object size, which is also a regression task. And secondly, consistency-based methods are another majority of TTA, such as MAMO, which optimize the prediction consistency across different augmented views of the input image. And their augmentation strategy typically follows the well-established practice in contrastive learning methods like MoCo and SimCLR. And these augmentations rely on techniques such as random cropping or resizing. However, these augmentations can disrupt the overall content of the image. That means the image's geometry structure like object size, locations, and relative layouts. While this may not affect the image level predictions like classification, it shall fail on more frequent tasks such as object detection and segmentation. For example, because in object detection, it requires the precise predictions of each object's coordinates and sets. So the destroy on image structure shall make these predictions incorrect. And lastly, alignment-based approaches conduct adaptation by aligning feature statistics like mean and variance between the target and the source data. While this approach is more general and applicable to a broader of tasks, it requires pre-calculating source statistics with access to the source data. This raises data privacy concerns, moreover. In this method, regularizes statistics to align with the source, but overlooks direct learning from the test data. This may lead to the limited performance in more complex scenarios. So in this work, our motivation is that how to develop a fully test-time adaptation framework for a variety of tasks for both classification and regression across image level, object level, and pixel level prediction tasks to boost real-world TTA application. To achieve this goal, in this work, we still build our method based on the general idea of consistency-based learning, but we extend it to a more unified architecture agnostic and task agnostic self-bootstrapping TTA approach for the versatile test time adaptation. The overall pipeline is shown in the figure. Given an input image X, we first perform augmentation on X to get X1 and X2. Then the both augmented sample X1, X2, and X are then both fed into the network, and then we can get corresponding predictions of the y hat 1 and y hat 2. Then we use the prediction y hat of the original image that termed as the strong view X as the target, and encourages the y hat 1 and y hat 2 to be consistent with y hat via a similarity loss. So this process enhances the predictions of the weak augmented or deteriorated image view, and in turn, this will feedback and improve the original predictions through shared model parameters. Here, the key challenge is that how can we design augmentation strategies so that it can preserve the image geometry, such as the object size, locations, and relative layouts. As these are essential to make this self-bootstrapping framework applicable to object level or pixel level prediction tasks. And meanwhile, we need also to enable that the augmentation could create a sufficient information gap from the original image to supply rich learning signals for our self-bootstrapping learning. So to this end, we start from Fourier augmentation. As a Fourier augmentation is more likely and has the potential to provide rich learning signals and meanwhile keeping geometry structure. To be specific, given image X, we first perform fast Fourier transformation, FFT, and to get the corresponding amplitude and bit component. Then One can conduct augmentation operations on the amplitude component and phase component, like phase shifting, amplitude exchanging, and masking. And after that, to perform an inverse fast Fourier transformation to get the augmented image. Based on the idea of Fourier augmentation, we first conduct some analysis on how common domain shifts manifest in the frequency domain. Before starting this, I first introduce REPSD metric. The full name is readily averaged power spectral density. It measures the information power of a given image across different frequencies. To be specific, the RPSD is calculated on the amplitude component. For example, in this amplitude, the pixels on each centered rectangle, such as this green rectangle, share the same frequency. And then the average value over this green rectangle denotes the IPSD at this frequency. And generally, the higher IPSD, the higher information power. And we plot the IPSD curve of images from different corruptions of IMNET C and IMNET rendition. From the figures, we found that the domain shifts in frequency domain can generally be categorized into the following groups. That has a high frequency increase, such as noise corruptions, and high frequency degradation, such as the blur corruptions, and low frequency degradation, like the contrast corruption, and also and some minimal changes. On some corruptions, there are minimal changes across all frequencies, such as the snow and the frost weather changes. So based on these observations, we then give our following design motivations. The first is low frequency masking contributes more for SPA. This is because images generally exhibit high absolute RAPSD value in the low frequency range. Thus, the RAPS difference before and after we apply a low frequency mask is relatively large, making the random low frequency masking an effective way to supply sufficient learning signals, no matter whether amplitude shifts degrade or remain unchanged. And moreover, the low frequency mask direction also often aligns with the domain shift direction. That is, both low frequency mask to lower the RAPSD and the domain shift on many corruptions shall decrease the RAPSD. So this is the same direction. And the second motivation is that the high frequency masking yields limited gains in SPA and even slightly hinder adaptation. This is because images at high frequency typically show very low absolute RAPSD value. Especially for blur corruptions that at high frequencies its IPSD already degraded. In this case, masking high frequency can only provide very limited learning signals. And moreover, masking on high frequency is also runs at the opposite direction with some corruptions like noise corruptions that increase. For these noise corruptions, it shall increase the high frequency RAPSD and thus may slightly hinder the adaptation performance. Now, our first augmentation strategy is low frequency masking, and we get sufficient learning signals at low frequencies, but we still miss learning signals at high frequency. Therefore, we also inject the noise into the original image to increase IPSD value at high frequencies. Although this is in contrast with amplitude shift directions of some corruptions like blur corruptions, noise injection is still an effective option because we have no other choice to create information gap as learning signals at high frequencies. And this is still improves overall adaptation performance. Then overall, our augmentation strategy in frequency domain is shown in figure E, where we decrease the RAPSD at low frequencies and increase RAPSD at high frequencies to create information gap as our learning signals. So with these design motivations, our detailed augmentation strategy is as shown in this figure. Firstly, at low frequencies, we first perform FFT, the fast Fourier transformation on the given testing image X, and then get the amplitude component. We then shift the amplitude to make the low frequency components located at the center area, and then randomly mask the low frequency central area. After that, we use the masked amplitude and the phase component to perform inverse FFT to get the augmented image X1. Then at high frequencies, we directly inject Gaussian noise into the original image to get the augmented image X2 to supply learning signals at high frequency. So with the defined two augmentations, the overall optimization problem is given as this formulation, where RS is similarity loss and SVX is an active selection strategy. This SVX is introduced to ensure the reliable learning signals. Specifically on classification heights, we select only lodges that predicted from the original target wheel is larger than the weak augmented wheel to perform similarity loss calculation. This is because the original wheel is not deteriorated, and ideally it could have a higher prediction confidence. So that's all about the method part. Next, we see some experiments. The first results are on image level classification. Firstly, compared to entropy-based methods such as tint, eta, and SAR, SPI achieves the best performance, and SPI also offers the flexibility to handle regression tasks, while the entropy-based objects cannot. And secondly, compared to co-TTA, which also applies consistency learning between the original image and its augmented wheels, SPI achieves significantly greater gains. This fully highlights the effectiveness of SPI and demonstrates that our structure-preserving augmentations are able to provide richer learning signals within this framework. And thirdly, compared to augment, SPI does not require access to source training data for calculating the source statistics to achieve alignment, and thus is more general to be used in case of source data are unavailable. Even though SPI also achieves higher performance than augment, improving the average accuracy from 66 to 70. And lastly, the learning objective of SPI is in parallel and not conflict with existing objectives like entropy minimization and feature alignment. This allows it to be integrated with these approaches to enhance performance further, as demonstrated that SPI incorporating XMAD and SPI incorporating with XMAD and tint, which further improves the performance. And we also conduct experiments on 3D monocular object detection. This task aims to predict the 3D bounding boxes, including the locations and the size of objects using a single camera image. It consists of both classification and regression tests. Another experimental setting is continual adaptation for pixel-level image segmentation, where the model is continually adapted in multiple rounds. Both these two scenarios are challenging, but the results are consistent with results on image level classification, where SPI achieves good performance individually and can also serve as a plug and play module to boost the existing methods. This table evaluates the effects of components in SPI, unlike previous self-supervised methods and augmentation consistency-based TTA methods. They maximize prediction or feature consistency between the two augmented wheels. The key difference of SPI is we adopt a weak to strong self-bootstrapping learning paradigm, which learns from a weak wheel to a strong wheel. This unidirectional learning plays a crucial role in our TTA approach, as it provides more reliable learning signals, which are essential in TTA context. As we can see that without this weak to strong strategy, bidirectional consistency learning results in a drastic performance degradation. And secondly, the activation selection strategy in equation 2 also helps to filter out partially unreliable supervisions. based on the premise that predictions from the original image are more reliable than those from the weaker augmented image views, and thus results in promising performance gains. And thirdly, both our proposed low-frequency amplitude mask and high-frequency noise injection augmentation strategies are effective individually, and it achieves the best performance when applied together. The core idea in SPA is to devise image geometric structure, preserving augmentations to ensure the applicability for fine-grained tasks like object detection and segmentation. Here we also provide compare our augmentation strategy with existing geometry, preserving ones, including the grid style, the brightness, and contrast adjustment. However, none of these augmentations, they individually or combined, can effectively provide detail with rich learning signals. These augmentations are often relatively simple and are sensitive to the corruption type and struggle to perform stably across all corruptions, leading to limited overall performance. Here, we also compare with other combination choice of our designed augmentation strategies like random frequency mask, low frequency mask, and high frequency mask, and noise injection. But our results show that these baselines perform worse than our SPA. And moreover, it's worth noting that masking only on high frequency amplitude often get trivial solutions. Yes. This is because masking high frequency gets very limited learning signals because the IPS value is very small at high frequency. This is also consistent with our prior analysis regarding the domain shifts in frequency domain. Here, in this table, we also compare our proposed augmentation strategy with prior augmentations used in self-supervised learning and consistent-based TTA methods, and by using our self-bootstrapping learning framework. The augmentation strategies, including the image mask augmix, and the monocular augmentations and the SimCLR augmentations. Results in the table show that while prior augmentations can achieve considerable performance on image level classification tasks, they fall short for 3D monocular detection, where they often perform worse than the batch normalization adaptation. This is because these augmentations, like random cropping and resizing, disrupt the image geometric structure, making them unsuitable for finer dense prediction tasks. In contrast, our augmentations are geometric preserving and supply rich learning signals for weak to strong self-bootstrapping learning, achieving improved adaptation performance. Also, in this figure, we evaluate the hyperparameter sensitivity in SPA, including both the noise ratio gamma and the mask ratio m. We can see that SPA works well across a wide range of m and gamma smaller than 0.5 for image classification, showing its insensitivity. But for 3D monocular object detection, although the mask ratio m performs well within a broad range from 0.1 to 0.5, the optimal range of noise ratio gamma is narrower than that in the image classification, and the stable range of gamma under this task is smaller than 0.2. This difference is mainly because in NetC, the task is at the image level, and it does not strictly requires the content environments of the image, allowing for a higher gamma to provide richer learning signals. Well, in contrast, 3D monocular detection involves dense predictions where high noise levels could significantly disrupt the original image content, making it challenging for self-bootstrapping learning. Okay, that's all about the SPA work for task versatility. And beyond the task versatility, I also would like to briefly mention the device versatility, for which we devise a forward optimization TTA method, and the paper is titled Test Time Model Adaptation with Only Forward Passes. As we aforementioned that test time adaptation's good performance relies on the backward propagation and updating the model weights. This makes existing learning-based TTA methods infeasible to many real-world application scenarios. This is because, firstly, on many resource-limited or latency-sensitive devices, such as surveillance cameras and embedded FPGAs and mobile phones, due to the power and memory limitation, these devices may not support the backward propagation operation. And secondly, for efficiency consideration, the deep models often undergo a quantization process before the deployment. That is, the model is often quantized. The full precision trained model is often quantized with lower bits to 8 bits or 6 bits or whatever bits from its full precision version of 32 bits. But on these quantized models, backward propagation shall result in vanishing gradients, making existing TTA methods infeasible. And lastly, also it is also for the computational acceleration. Some GPU chips are tailored for specific models, and these models weights are non-modifiable once the model is deployed. All these natures making this in learning-based TTA method infeasible for many real-world deployment scenarios. So to address this issue and boost the TTA's device versatility and bridge the gap between the research of TTA and real-world deployment of TTA, in this work, our key motivation is that how can we remove the backward propagation process and avoid updating model weights during the TTA process, and meanwhile keep the excellent adaptation performance. So to this end, our straightforward idea is to replace the back propagation-based optimizers such as SGD and ADAM with the back propagation-free optimizers, such as there's other methods, Bayesian methods, and covariance matrix adaptation methods. In this work, we select CMA as our optimizer because it is more suitable for our TTA context and has much better empirical convergence to satisfy our online TTA demand. Even though it is still very hard for these backward propagation-free optimization methods to optimize a super high-dimensional problem, such as deep models. So in our method, instead of optimizing the model or normal layers of the model, we learn a newly inserted input prompt to reduce the dimension of the solution space to make the CMA optimization easier and feasible. Based on this motivation, we propose a forward-only prompt adaptation method. This figure illustrates the overall paradigm of our proposed FOA. We insert a learnable prompt at the input layer for continuous optimization. Then all online arrived testing samples will be fed into the model alongside the inserted prompt to perform forward propagation. Then the model shall output predictions, and we can calculate a fitness value according to the model outputs. Then the fitness can serve as learning signals to guide the CMA learner. Well, in this paradigm, the most key step is how to define a proper fitness function. As previous CMA optimizers are typically used in the offline supervised setting, while in our TTA, the learning process should be online and unsupervised. So unlike a conventional entropy metric in TTA literature, it is infeasible for our prompt learning. As entropy-only fitness fails to stabilize the CMA learning and will result in a collapse issue, that is, the CMA shall learn a collapsed trivial prompt solution. So to address this issue, in addition to the entropy metric, we further introduce a feature discrepancy fitness. Before we start the test time adaptation, we first calculate the classification tokens distribution statistics, including the mean and variance via the original source model. The source statistics are calculated via a few unlabeled in-distribution samples for only once. Once the source mean and variance is calculated, we keep it at frozen to regularize the distance between the corresponding classification tokens mean and variance of the target TTA model to align with the source mean and variance. So with this design fitness function, our FOA can optimize prompts via covariance matrix adaptation strategy stably during a long-term online TTA process. So what is CMA? So instead of directly optimizing prompt P as in gradient descent, the CMA optimizes a distribution of prompts to estimate where the optimal prompt should be located. As shown in this figure, CMA first sample K prompts from the estimated distribution. Next, given the potentially shifted test data, we perform forward passes with each prompt and rank different prompts according to the fitness value introduced previously. Then CMA will update the estimated distribution according to the ranking information of the key prompts. The detailed updated strategy is relatively complex, and I do not clearly introduce it here. Please also refer to the original paper if you are interested. However, prompt adaptation may be still inadequate. This is because at the beginning of prompt learning, the prompt is randomly initialized and shall affect the initial model performance. In this case, we further conduct back-to-source activation shifting at the feature level. It directly shifts the activations along the direction from the out of distribution to in distribution. This moves the activation center of the test data closer to in distribution for better domain alignment. Where the source center is the same as the mean vector that we pre-calculated on the source samples for the fitness function calculation. And the target center is online adapted on target samples using an exponential moving average strategy. Here are some main results of our FOA work. On the full precision model, we first compare with the BP3 methods, including the LAME and the T3A. These methods update only the classifier and often struggle to enhance the performance with the limited learning capacity. In contrast, FOA use forward passes for prompt optimization, achieving much better results as shown in the table. We also verify that FOA can even outperform the BP-based methods like Tunt and Cota using only forward optimization. We attribute this result to our loss design and our back-to-source activation shifting. Next, on context models that are incapable of backward propagation, we show that FOA is less affected by using only forward passes. It consistently improves the performance on both the 8-bit and 6-bit context models, offering a solution to adapt context models deployed on devices. And one interesting thing is that actually FOA on 8-bit context models can outperform BP-based Tunt and SR on full precision 32-bit models. This fully verifies our superiority. And in summary, FOA eliminates the need for model updates and gradient backward propagation. It largely reduces the memory overhead while achieving better performance than previous thought tests. This makes FOA particularly suitable for real-world applications and especially for use with context models and low-power edge devices to boost the TTA's device versatility. So the overall conclusion of today's talk is that we discussed the versatility of test time adaptation in two aspects. The first is task versatility, for which we devise a self-bootstrapping TTA framework with Fourier augmentation strategies to supply rich learning signals and also keep TTA compatible to various tasks and models. And then the second one is device versatility, for which we devise a forward-only learning-based TTA method that ensures TTA can be applied to various resource-limited embedded systems. And both of these two aspects work together to boost the TTA's versatility and facilitate larger-scale deployment of TTA in practice. And that's all my presentation today, and thank you for your attention.